Alright, welcome to Lab 4. So the goal of this lab first is that we want to examine the motion of a spring mass system while it's swinging in an arc to analyze the motion and examine the oscillations to confirm that there's no loss of energy. So we are going to go ahead and do a comparison between motion graphs and energy graphs, and then we're going to go ahead and, from a computational model, go ahead and predict the motion and see how similar it is with the actual motion. And this is going to be applying Newton's second law. So some general things to know is firstly the energy principle, which is that a change in energy is equal to the work done by the surroundings. And the change in energy is the sum of the change in the kinetic energy, the sum of the change of the gravitational potential energy, and the sum of the change in the spring potential energy. Lastly, an extension of Newton's second law is going to be the momentum principle that we're going to be applying, and you can see the equations there. So going ahead and plugging the video into Tracker, I went ahead and generated this, and went ahead and took frame by frame measurements, and went ahead and then used this for analysis. So the initial considerations is that there was zero velocity as it was released from rest. The position I was given as the initial position was negative 0.107 meters and negative 0.636 meters. And then the mass was given as 0.402, so plugging all of these in. Then the next thing that we had to do was actually calculate a couple things. One would be the K constant using the period, and then the other would be actually the base length of the spring. And I did this by go ahead and applying the period is equal to 2 pi the square root of m over k, and using the previous graphs, I measured the period. And once I did that, I went ahead and recalculated it to find a k value of 5.485. And then using force balance, you can go ahead and find what the normal length of the spring is after you find that spring constant. So then plugging all of these in, you go ahead and plug in the relaxed length of the spring constant, and then go ahead and start calculating your L, which would be the position of the ball minus the position of the spring, and get your L hat and your S. And then from there we go ahead into the energies, which would be 1/2 the mass of the ball times the velocity squared. The gravitational potential is given as the mass of the ball times gravity times the height, and then the spring potential energy is given as 1/2 times the K constant for the spring times the S, or the displacement from the initial state, squared. Then we sum all those, get the total energy. Then the entire motion took about 9.47 seconds. So go ahead and defining the initial energies, and then going ahead and calculating the forces of gravity, the spring, and then those are the only two forces acting on the system. So we go ahead and find our F net. Then we apply the momentum principle, the extension of Newton's second law, to go ahead and get the change in velocity, and then update the object's position, to then re-update the position of the spring. And then we calculate the new energies by just going ahead and calculating the energy at this individual point, and then subtracting the initial energy. So whenever I actually went ahead and plotted this, these are the two plots I generated, and you can see that it's fairly accurate, but it's also fairly off. We see that the periods are longer in the actual experiment rather than the model, and that just means that there were some variations and everything. When we look at our actual energy graph, we can conclude that energy was conserved, and that's because the orange line remained at 0, which is the change in energy. So that means that there was no work done by the surroundings, which is what we would have hoped to expect from our model. And then lastly, the period between the x and the y are different, and what that means is this isn't moving in a perfect circle, rather it's moving in some kind of bizarre circular or elliptical-like motion. And we found by the same method as before, the period of x was 1.701, and that's mainly affected by gravity and length. It's acting like a pendulum. And then the period of the y is the same thing as we did up here, except now we're going to go ahead and find the period for the other graph. And once I went ahead and computed all those numbers out, I got 1.432, and this is because it's mainly affected by the mass and the stiffness of the spring. Thank you.